Hello and welcome to another episode of Mr. Boskin Does Some Math. Today we are doing illustrative math, grade 8, unit 8, lesson 9. Our first problem here shows a clock. Consider the tips of the hands of an analog clock that has an hour hand that is 3 centimeters long and a minute hand that is 4 centimeters long. What is the farthest apart the two tips can get? Well, if this is on the 9 and this is on the 3, that's as far away as those 2 points can get. And that will be 7 centimeters away, because from here is 4 and then 3 more to this tip. What's the farthest away the two tips can get? 7 centimeters. What's the closest the two tips can get? Well, at midnight, both hands of the clock will be pointing straight up and down. Well, straight up. And the tip of the two hands of the clock will be 1 centimeter apart. Are the two tips ever exactly 5 centimeters apart? Well, the closest they get is 1 centimeter and the farthest away they get is 7 centimeters. So at some point of their moving closer and farther away, they do have to pass. Yes. Teach me to talk while I'm trying to write. Yes, they do have to be exactly 5 centimeters apart at some point. Proving the converse. Here are 3 triangles with 2 side lengths measuring 3 units and 4 units, and the third side of unknown length. Well, this one right here is a right triangle, so we can use the Pythagorean theorem that we've been using. 3 squared plus 4 squared equals z squared. 9 plus 16 equals z squared, which means 25 equals z squared, which means 5 has to be equal to z. So this length is 5. Now let's look at x and y. Y, this is less than a 90-degree angle, so is this line segment going to be longer or shorter than 5? Well, this acute angle means those are squeezed in. This is going to be less than 5. So y has to be less than 5. And x, this is greater than a 90-degree angle, so that is spread out. So that is going to be greater than 5. Okay, sort the following 6 numbers from smallest to largest. Well, the closest they can be is 1. Now, what else do we have here? We have x, y, and z. Y has to be less than 5. Ooh, I can do this with less than and greater than signs. 1 is less than 5. Whoops, that was supposed to be a y. 1 is less than y, because y is less than 5, which is less than 5, and 5 is equal to z, and that has to be less than x, and x has to be less than 7, because if this were a straight angle, it would be 7 units. Okay, so that's those 6 values in order, but 5 and z are equal to each other. Ooh, and are you ready for more questions? These are always fun. The related argument also lets us distinguish acute from obtuse triangles using only their side lengths. Decide if triangles with the following side lengths are acute, right, or obtuse. In right or obtuse triangles, identify which side length is opposite the right or obtuse angle. So for these, we can do well, let's first say in right or obtuse triangles, identify which side length is opposite the right or obtuse angle. Well, that needs to be the longest side, because if it's a right angle, it's the hypotenuse. If it's an obtuse triangle, the longest side is opposite the obtuse angle. So C always needs to be our longest side. On this one, Y is our longest side. On the second one here, Y is also the longest side. On the last one here, X is the longest side. So if we did a squared plus b squared equals c squared, like we would for the Pythagorean theorem, we would have to do 8 squared plus 15 squared. Does that equal 20 squared? I'll do it over here so there's space to do each one individually. 8 squared is 64. 15 squared is 225. And 20 squared is 400. Um, 64 plus 225. Is that equal? No, 64 plus 225 is less than 400. Now let's check our next one here. 8 squared plus 13 squared. Is that equal to 15 squared? Well, let's check. Again, 8 squared is 64. 13 squared is 169. And 15 squared is 225. Well, 169 plus 64 is 233. So that's actually greater than 225. Now our last one here, the 17 would have to be C, so 8 squared plus 15 squared, is that equal to 17 squared. 8 squared is 64. 15 squared is 225. And 17 squared is 289. Well, 225 plus 64 is actually equal to 289. So this one right here has to be a right triangle. For this one, the square of our other sides is greater than our actual side. And for this one, the square of our other sides is less than the square of this. So what does that mean? Decide from looking at that if the triangles are right triangles or not. So let's look at the first one here. If this were a right triangle and we had side lengths of 8 and 15, and we found out what this length was, if it were a right triangle, it would have to equal this side squared. However, what we got is less than this side squared, which means if these added together are less than this, that means this is too much, this is too long for it to be a right triangle. If this is too long, then this has to be more than a 90-degree angle. If that's too long, this angle has to be larger than 90, so this one has to be an obtuse triangle. This one, these are too much, which means this is too small, so this one has to be an acute triangle. Calculating legs of right triangles. Given the information provided for the right triangles shown here, find the unknown side length. So these are right triangles. Which angle on here is a right angle? It looks like that one. So these are our legs. So 2 squared plus a squared has to equal 7 squared. 2 squared is 4, plus a squared equals 49. Take care of this 4, subtract 4 from each side. A squared has to equal 45. To isolate the a, we take the square root of each side, so a has to equal the square root of 45. This one is a little trickier. Where is our right angle? This is our right angle. If this is x and this is x, that means this is an isosceles right triangle, but both of these are legs. So x squared plus x squared has to equal 4 squared. X squared plus x squared is 2x squared, has to equal 4 squared is 16. Now we want to isolate our x. First we've got to get rid of this 2 that's hanging out over here. This is kind of new, but 2 times a variable. How do we undo multiplying by 2? We divide by 2. So x squared is equal to 8. If x squared is 8, to isolate the x, we have to take the square root of each side. X is equal to the square root of 8. The triangle shown here is not a right triangle. What are two different ways you change one of the values so that it would be a right triangle? Sketch these new triangles and clearly label the right angle. So this is not a right triangle. We want to change one of the values. So what if we wanted to change this value? This is currently the longest side, which means that a squared plus b squared has to equal c squared for it to be a right triangle. So if we have a right triangle with legs of 4 and 6, what does our hypotenuse have to be? 4 squared plus 6 squared has to equal c squared. That has to equal what this is. 4 squared is 16. 6 squared is 36. Has to equal c squared. 36 plus 16 is 52. Has to equal c squared. So the square root of 52 has to be c. So this side length would have to be the square root of 52. And that would have to be a right triangle. Well, let's try a different one. What if we changed this? Well, if we were to change this, this angle looks closest to a right angle, so this would still be our hypotenuse, and this would be legs. So we would have a triangle with one leg of 4 and a hypotenuse. That looks kind of like a Y. One leg of 4 and a hypotenuse of 7. Well, 4 squared plus whatever this is, b squared would have to equal 7 squared. 4 squared is 16 plus b, we don't know what it would have to be for it to be a right triangle, has to equal 7 squared, which is 49. Subtract 16 from each side. B squared has to equal 49 subtract 16, which is 33. So B has to be equal to the square root of 33. Now, this is a right triangle. Okay, our quick summary. What if it isn't clear whether a triangle is a right triangle or not? Here is a triangle. We don't know if it's a right triangle or not. Is it a right triangle? It's hard to tell just by looking, and it may be that sides are not drawn to scale. If we have a triangle with side lengths A, B, and C, with C being the longest of the three, then the converse of the Pythagorean theorem tells us that any time we have a squared plus b squared equals c squared, we must have a right triangle. Since 8 squared plus 15 squared equals 64 plus 225, which equals 289, which is 17 squared, any triangle with side lengths 8, 15, and 17 must be a right triangle. Together, the Pythagorean theorem and its converse provide a one-step test for checking to see if a triangle is a right triangle just using its side lengths. If a squared plus b squared equals c squared, then it has to be a right triangle. If a squared plus b squared does not equal c squared, then it is not a right triangle. This is a nice, easy way for us to test whether or not something is a right triangle just by looking at its side lengths. This has been another episode of Mr. Boskin Does Some Math. Thanks for tuning in. See you next time.